Welcome, everyone. My name is Teresa, and I'm going to be your moderator for today's webinar. Before we dive in, a quick reminder that today's session is being recorded, as they always are, and we will be sharing the recording with registrants. Please go ahead and use the question panel to submit your questions. If we can take those throughout the presentation, but we definitely have time at the end to handle a couple. We have also received a few during the registration process, so we've got those queued up. But I first wanted to say thank you so much to Jaden and Andy for joining us today. Jaden Hess is the principal security engineer on the cryptography team here at Trail of Bits. His specific area of expertise include HSM applications, zero-knowledge proof systems and circuits, and of course, trusted execution environments, or TEEs, as you will get used to hearing us say 1,000 times today. Andy Campbell is the head of product at Applied Blockchain. He's one of the most experienced blockchain development studios in the industry and the creator of Silent Data, the first privacy-enabled Ethereum layer 2 to join the superchain. Applied Blockchain has been delivering enterprise solutions for more than a decade with deep expertise in blockchain and cryptography and over 5 years experience working with privacy technologies such as zero-knowledge proofs, multi-party computation, trusted execution environments, including Intel SGX, Intel TDX, and AMD SEV SMP. So we are so glad to have you both here to explore how TEE's projects can adapt through secure architectures, layered privacy models, and resilient attestation approaches, keeping confidentiality and trust at the core of next-generation blockchain infrastructure. So, Jaden, without further ado, I will pass to you.
Okay, thank you. So we're going to go through basically just a quick overview of how the attacks, the recent DRAM-based attacks against TDX and SEV work, and then look at how those attacks impact each system slightly differently, and maybe talk a little bit about, what the underlying causes are and the broader effects to TEs in general, and then talk a little bit about, what do we do from here? How secure can TEs be? What threat models do they make sense under? What can be done to use them more securely? Okay. So the two attacks that have been sort of in the news recently are known as Wiretap and Battering RAM. The sort of core of both of them is that they're physical attacks against trusted execution environments that use server CPUs with some sort of architectural extension to create a trusted execution environment. So the idea of a trusted execution environment is that you should be able to run code in such a way that the host operating system cannot observe secret values stored in that code, and that you can prove this fact remotely to other parties. These physical attacks mean that someone with physical access to the device is able to extract secrets and forge attestations to impersonate enclaves or steal secrets out of genuine enclaves. Now, both of the attacks are actually out of scope for the threat models for Intel and AMD because they both sort of write out physical attacks in general. So you can see that even in like the original documentation for SGX, TDX, and SEV SMP, there are little notes that say that some physical attacks, such as cold boot attacks, are prevented, but active attacks against the DRAM bus are not. And so the assumption here is basically that there are some sorts of attacks which maybe are perceived to be easy in the sense that you can just take a DRAM DIMM out of your motherboard, like freeze it literally, insert it in a different computer, and then read out the bits. This was thought to be, in some sense, easy and worth protecting against using memory encryption. Things that relied on interposers in the DRAM bus actually tampering with the high-speed bus as it is in use were thought to be kind of very difficult, required advanced attackers with all sorts of potentially bulky equipment, and so they were ridden out of the scope of protection. And we'll talk about sort of why pragmatically in a bit. So what are the actual attacks here? The actual attacks are based on the fact that SGX, TDX, and SCVSNP all use some sort of in-place encryption with no expansion. So this is actually not true of older sort of consumer SGX, but for so-called scalable SGX and TDX and SCVSNP, there's no IV or MAC, if you're familiar with these components of normal authenticated encryption. Instead, encrypted data has to fit in exactly the same space that the plaintext did. So when your trusted execution environment is computing on some data, it's storing secret keys to memory, for example. It is encrypting that data in place using AES XTS generally, and then that data, because it has to fit in the same spot, same length in memory that the original data did, always has to be deterministic, because in order to randomize encryption, you need to add some extra random IV in front. So what this means is that you end up with a deterministic encryption mode where if I encrypt, 1, 2, 3, 4, 5, and then change that and then re-encrypt it later at a particular location, the ciphertext looks the same. So while ciphertext cannot be kind of correlated across memory locations, across addresses, pointers, they can be correlated across time at a given pointer. And so you can build a library of ciphertexts where if I know a plaintext and can cause that to be encrypted, I can see what the ciphertext is and then see if that ciphertext ever reappears, and thus know that the particular plaintext is being stored. It turns out that this is sufficient to break pretty much all cryptography. There are mitigations that could be applied, but in general, you can imagine that the particular knowledge of whether a certain ciphertext shows up in the middle of a cryptographic computation is sufficient to leak secret keys out of your computation. So, for example, if you have a TLS private key for a TLS certificate, then it's possible that an observer who can see the ciphertext can basically watch the signing process and use information gained from this deterministic encryption to extract your secret key. So it turns out that, as we said, like the encryption is kind of not great. It requires sort of architectural protections around it to prevent attackers from reading ciphertexts. And so all of these systems have some sort of architectural protections, right? Like the CPU sort of in its normal operation prevents you from reading even ciphertexts from memory locations that are not in the current trust context. But the problem is that there is no physical measure to prevent sort of reading and writing from context outside of in any particular context. Also, TDX has cryptographic integrity mode that makes like a lot of these attacks a little bit more difficult, but sort of only a little bit more difficult. And in most of these contexts, the attacker is allowed essentially infinite retries. So things like Max with 28-bit security kind of just increase the amount of time it takes for an attacker to carry out the attack rather than preventing the attack outright. So, despite what people thought, the ability to attack these fast DRAM buses, right? These things go 2, 3, 4 gigahertz or something like that. They actually turn out to not be quite as expensive as one might expect. It turns out that the reason for this is basically that you don't need to actually read and write data at native DRAM bus speeds necessarily. So these things don't need to be fully general DRAM interposers. They can do sort of specialized single purpose things. And that's sufficient when combined with control over the host operating system and hypervisor to get secrets out of your enclaves. So Wiretap is just a passive DRAM bus analyzer. The authors basically tuned the bus speed way down, used off-the-shelf logic analyzers to read data off the bus and just see if there are ciphertexts that match the ciphertext dictionary they had built up. This needs not capture all of the data on the bus because the host OS has very fine-grained control over the stepping of the trusted execution environment, which means that by very precisely timing when the logic analyzer starts capturing and when the OS kind of kicks off the VM or context switch into the VM, you can only capture a very small amount of data and know that your target reads and writes are happening right in that spot. Battering RAM is also quite interesting. It basically creates a physical memory alias where two logical addresses in the CPU correspond to the same physical bits on the DRAM DIMM. And this actually happens essentially totally passively. So there doesn't need to be any fancy high-speed logic going on in this DIMM. It's quite cheap. It just sits in between your DRAM and your DRAM slot and allows a untrusted program on the host computer to use this aliased memory in order to do the reads and writes that are necessary to compromise the integrity of the TEs. It turns out that Wiretap was able to be extended relatively straightforwardly to DDR5 RAM. Initially, these were just DDR4 based attacks. Battering RAM is harder, significantly harder to extend to DDR5 because the DDR5 bus is small, and it turns out there's no single bit that you can wire to ground to cause memory aliases. And so for DDR5 systems, which includes all TDX systems, the only way to carry out an attack right now is with this sort of bulky logic analyzer setup that requires some sort of external components that's a little bit noisy. The nice sort of inline interposers don't work quite yet, but there's sort of nothing preventing it in generality from working. Okay, not all TEs are affected the same way. So it turns out that SEV-SMP allows for active extraction of secrets from confidential virtual machines that are currently running. So if you're running, say a secret blockchain node inside of a AMD SEV-SMP machine, and you have an active logic bus analyzer sitting on that CVM, then one can potentially extract secrets out of that CVM. On the other hand, TDX is actually affected much more dramatically, where because the quote enclave, the thing that does that proves to third parties that a TE is running sort of a valid program, an integrity protected program, because that attestation code sits inside of the TE system that uses the main DRAM memory, it actually allows for extracting attestation keys, which means that there's sort of an attack once, use many times problem, where at any point someone can extract an attestation key from a TDX machine and then later impersonate that TDX machine, even when they no longer have physical access to the machine. So this is quite different from the AMD system, which uses sort of a separate secure processor to hold those attestation keys. Okay, so what can be done? One thing is that it's not secure to have literally anyone host your TE and assume that just because it has a valid quote that no one is reading your secrets out of it. So there needs to be some sort of binding to a particular cloud provider or hoster, which can be done via TPM bindings or via restriction to particular known CPU IDs. The other things that can be done are to use systems with sort of semi-trusted hypervisors, where a lot of these attacks require the ability for an attacker to have the virtual memory manager or hypervisor access to the TE. If you can rule that out by giving it to some trusted third party like AWS, that rules out a lot of these classes of attack. The other things are just physical security, right? Make a tamper evident chassis, wipe all your provisioning keys if someone opens it. And then, this has all been about this sort of scalar, like server class CPUs. There's other custom hardware that one could use or build that does not have these problems because it has memory integrity protections like the old consumer SGX did. This causes various cost and performance trade-offs, though. Okay, I will hand it over to Andy now to talk about what applied blockchain is doing, in this new world of DRAM attacks.
Thanks, Jaden. Thanks very much. So yeah, as was mentioned by Teresa at the start, so we're applied blockchain. So we've been in the space for 10 years, and we wanted to give. We've been working with TEs for over 5 years. We've also done work with ZKP and MPC, and we're familiar as well with FHE, and really we wanted to give our perspective as a builder that's using these technologies of what's changed and what stays the same. So essentially what I'll be looking at is our perspective of what guarantees cannot be provided by TEs, what guarantees do TEs still provide, and what alternatives are there to TEs for blockchain privacy, and what are some of the trade-offs of those technologies. So what guarantees cannot now be provided through TEs? So if someone's making the claim that a malicious actor with physical access to the machine cannot access runtime data, that's an incorrect claim, right? That is it's wrong to make that claim. Another claim which is not correct is that remote attestations prove that a malicious actor with physical access to the machine doesn't have access to runtime data. But I think the important thing to mention here is what Jaden said, which is these claims were always essentially out of scope according to the hardware manufacturers. So both Intel and AMD already ruled out these claims. So really what's changed in this perspective is that this has gone from theoretically ruled out to practically ruled out as well. So if someone was building with these assumptions, they were always essentially building under false assumptions. So if we can't make these claims, why are TEs still useful, or are TEs still useful? So I think there's still some very useful claims around TEs. So a malicious workload provider cannot access the data when using a third-party host. That's still true, right? As long as the workload is solid. So here the workload provider is really the application developer for the TE. As long as that TE workload is actually solid, then even a malicious workload provider cannot access that data as long as they're using a trusted third-party host that isn't colluding with them in some way. A malicious actor within the host organization without physical access machine also can't access the data. So if you've got an application running in an enclave and a employee which has perhaps remote access to that machine and to that operating system, they still can't access the running guest or the running enclave that's running on that machine, assuming that workload is solid. And this is important because it's tempting to view the host of the data as one entity and one actor, but cloud providers aren't really one actor, right? They're a series of different actors. So you have a lot of people that might have some kind of sysadmin access to a machine. There are less people that then have physical access to that machine, and it's also a very deliberate attack. There is, the hardware itself is portable, but it has to be a very, it's hard to do this in a non-transparent way, right? It's hard to do this and not get caught. You would guess you would hope with a lot of the cloud providers and hardware providers. And finally, remote attestation can verify that the workload provider cannot access the data. So if you're developing an enclave application, like Silent Data, for example, so what we're doing with Silent Data is we deploy the application, and we're still able to say to our clients, we can't access the data, right? Like we can still make that claim because we don't have physical access to the host, essentially. So we still think the TEs are essentially hold up to their original premise. There may be some people that had some false assumptions around TEs that they protected against physical attacks or all physical attacks. But as long as you have the correct assumptions, not too much has changed there. It's really gone from a theoretical, these attacks have ruled out, to a practical, these attacks are really are possible and out of scope. So the impact for privacy in blockchain systems is that a TE attestation alone is not enough to share data with an untrusted third party. So if you were developing a completely permissionless blockchain system where you were relying on a TE to protect the data, so let's say you were running, let's say, a version of Zcash that instead of using ZKP, it used TEs, and anyone can run a node. And if a peer gets an attestation from another peer, it shares the data with that peer. That application is not considered secure because you only need one of those peers to be malicious to essentially extract the data, right? But as mentioned before, I think that was already really an incorrect application to develop. What's now required, if you're going to build in a blockchain system, the node operators need to be permissioned in order for this to have protection. So there needs to be not only a guarantee that a TE is being used and that the application running on that TE is secure, but also that the host of that data needs to be somewhat trusted, right? This needs to be a somewhat permissioned system. And the other thing that's very important, if you want to actually prove some guarantees around the security, is that the node operator and the host should be split. So if you've got the developer of the application, like us at Apply Blockchain with Silent Data, we further secure by deploying on third-party infrastructure, right? We're not self-hosting. Essentially, we're using providers for our enclaves. And then finally, the different technologies in the space, which I think are really worth considering, because I think it's important to think about what different compromises are out there with different technologies. We essentially came to TEs via these different technologies. So we spent a lot of time looking at particularly MPC and ZKPs. And I think all of these have various limitations, including FHE as well. So all of these technologies are essentially built to support computation on private data. So have data remain private and be able to do computation on that data. So that's true across the board. One of the things that you can do in TEs, and the reason that we think TEs are interesting, is that within the TE, you essentially have, you can work with data in the same way you would work with plain text data, even though it's encrypted from the outside. So what this means is that you can do use cases like sharing dynamic data that you can't essentially do with FHE and ZKP and MPC, right? They're not really supposed to solve that use case. So let's say you have a use case where you want to say, okay, we have data and we want to share a subset of the history or the entire history now with a regulator across all parties, right? It's a mixed use data. It's a mixed use data set coming from multiple parties. The other technologies aren't really built for that. They're built a lot more for computation. Also, if you want to power smart contract privacy, I think MPC is not so fit for this. MPC is really coming for different use cases. You can do those things with ZKP and FHE with some limitations, but you can power smart contracts. And then finally, if you want to abstract away from privacy within Solidity or a non-bespoke tool set, so let's say you don't want users to have to write circuits or develop a bespoke MPC application or have a custom set of tools, then it's very hard to do that with these other technologies. You need something that's going to wrap the entire system to be able to do that, and we think that's why TEs are very useful. So in our view, there's still a really strong place for TEs. We don't view too much has changed here in terms of the assumptions around TEs, but it may be the case that some parties were making perhaps over reliant on TEs. If you are doing something in the completely public space and really relying on that as the only mode of security, I think that does open up a weakness within systems. But it's worth saying that really people shouldn't have been doing that. Okay, thanks very much, and I think we're going to move to a Q&A.
Yes, thank you so much. Appreciate both of you and your perspectives. We do have a couple of questions that came in through the registration, so I'll start with those. I will just add them to the stream and then I will read them out loud. I am particularly interested in threat model analysis between entirely closed source services and partially open source products where the trust is split. And they want to know what types of considerations you suggest to be examined when deciding on which type of TE product to use for the given case.
Yeah, I can talk about this a little bit. So, well, for one thing, it's not entirely clear to me in what sense TDX is more open source than something like Nitro. I mean, the actual hardware implementations, of course, are quite secretive and require extensive reverse engineering. At the hypervisor level, there is some difference where it's possible to, write your own hypervisor or in practice use something open source like QEMU. But this difference is not really visible to the relying parties of an attestation, where the person who is actually verifying the attestation doesn't see any difference. I mean, from the perspective of like ability for researchers to actually get their hands on the system and attack it, there may be an issue there. But as we've talked about, physical security is sort of weak across the board. So probably we shouldn't be relying on the physical security of the systems in general. I think that the difference in threat model, from my perspective, is that there are quite a lot of attacks, even ignoring problems with the actual TEs, that are accessible only to someone with access to the hypervisor, right? So in particular, all of these attacks, but also a whole host of side channel attacks, rely heavily on the ability for someone to single step through the target program or otherwise like observe memory access patterns. And so while there's some like security through obscurity going on with something like Nitro, the ability to prevent the sort of application developer from getting that sort of nuanced architectural information out of the execution of the CVM means that the attack surface is way smaller. I mean, there's just a huge attack surface if you have access to the hypervisor.
Great. And the second question we got was, you kind of addressed it, Andy, but do you all feel, or can you elaborate on the FHE solving for any of these issues?
Yeah, in my view, it's just a different use case. I mean, it really depends on your application, right? If you're going to, in theory, if you're going to write an FHE application and that FHE application is secure, you shouldn't really need to run it in a TE. It's just that it's not as flexible, right? That you can't just take a generic application and say, okay, I'm gonna just fully homomorphic encryptionize it, right? Or like just turn it into a ZKP. Like a lot of those technologies are a lot more limited. Yeah, I think it's just a completely different tool set with a different set of use cases.
I'd also add in that FHE has a lot of challenges around integrity, right? So you can get confidentiality, but TEs are nice because you know that it's doing the right thing. FHE is very hard to get that property.
Okay, we are at time technically, but we probably have time for one more question. I will leave it up to the speakers, Andy or Jaden, to pick one of the questions from the chat, if you don't mind. It's a question about MPC-based key management. There was some feedback about AWS being a black box, which we kind of already addressed. Anything?
Just reading through.
Yeah, I mean, I think, without a ton of time to read through all of these questions, MPC also, it has performance penalties. And so if you're trying to do something like LLM inference, which a lot of people are trying to do, that is quite difficult to do in MPC. It might be better for blockchain solutions where you're trying to just execute smart contracts, but there's a difference between just executing smart contracts in MPC versus executing a whole blockchain node in MPC, which is much more difficult, especially if you want to maintain compatibility with something like Ethereum.
Yeah, I think MPC is particularly limited because really with MPC, often what you're trying to do is have a group of parties and then have no one party have complete access to the data, right, or have complete access to everyone else's data. So I think that there are some interesting use cases for MPC. It just tends to be a bit more limited, and I think not well suited to blockchain applications on the whole. So you can't build like an EVM in MPC, or like you can't build those kind of generalized applications. I think that there's also a question around like MPC key management and generation. I think the challenge that you have is that you always need the data somewhere, right? So whilst you can do things with MPC key management, it's then what are you doing with that key afterwards, or what is it that you have to do? So beyond simple use cases of encryption, decryption, which are still useful, right? Like if you're trying to run an MPC wallet or something like that, those are still useful applications. But beyond that, it becomes a lot more challenging when you try to actually express different privacy use cases in MPC, I think.
Amazing. Thank you both. I know we're a little bit over time, so I appreciate it. And I will let everybody get back to their other meetings, but we did include, we will be sending out the recording within the next 30 minutes. Slides will be available as well. If you do have any questions, please feel free to find us. I've dropped contact information into the chat. Thank you, Andy. Thank you, Jaden. And you all can look forward to some future updates from both of us. Take care, everyone.
Fantastic. Thanks very much.